Let's start again and continue from where we stopped. That's the point. We bring the sources and receivers to a common datum level. And my question, would we apply static in marine data? No, there is no static in marine data because the sources and receivers are usually already in a common datum level. So static is not applied in marine data. So in marine acquisition, seismic acquisition, then in marine, static is not applied. The reason being the sources and receivers are already in a common datum. They are on common level. And usually the bottom layer, the first layer we encounter in marine is hard rock. So static is applied most often in Oman, where the upper layer is soil layer, sand dunes, it's problematic. You will get a lot of jiggering traces, the traces are not aligned. You will struggle a lot. In PDU, the company which is doing processing for them is called CGG. They have a dedicated whole department to do static correction. It's really problematic thing because, as I said, Oman surface environment is where the oil fields are. It's made of sand dunes. So we bring the data to a common datum. As you see here, we see the upper layer is low velocity layer V1. The lower layer where the rocks get consolidated, get hardened, get a sedimentary or igneous or even metamorphic rocks. It's not a soil layer. That's before static, and after static, that's how it becomes. So type of surveys, as I said, seismic surveys can either be conducted in marine or inland. Inland survey, the equipment we use to record the data, it's called geophone, whereas in marine data, we record through an equipment called hydrophones. The main difference is that geophones, they are sensitive to velocity variation or displacement variation, whereas hydrophones, they are sensitive to what? Pressure variation. That's true. You are already with the exam. So yeah, hydrophones are sensitive to change in pressure. It means they can record or they can analyze bulk modulus. Shear modulus cannot be recorded. Shear modulus, and what velocity type can bring information about shear modulus? What velocity? P as well as S. S equals young shear modulus over square root of shear modulus over the density of the rocks. So shear modulus is totally not recorded in marine data. Hydrophones, they cannot record S-wave velocity. How we can then record probably S-wave velocity in marine data? What we can do? Huh? Another method? Let's say I want to record seismic data. I'm concerned about seismic data. I want to record as well S-wave. Use what? A compression? What should I change about my acquisition parameters or acquisition configuration? Huh? That's true. Make your big geophones, but plant them where? On the sea bottom. And that's what's done in North Sea. In North Sea, they acquire seismic data every 6 months. Every 6 months, they acquire seismic data. It's cheap because sea, you can acquire easily. The main problematic part is how to put or plant the geophones. They have the geophone planted on the bottom of the sea. Ocean bottom seismometers, they call them, OBS. Ocean bottom seismometers. They are recording both P wave as well as S wave. Because recording these two brings you a lot of information. One of the information you can bring if you record both S and P wave is whether the rock contains fluid or not. Recording alone, the P wave cannot bring you a lot of information rather than only how the rocks are changing, how many layers, and what are the characteristics of each layer. What is the density and velocity variations within those layers. However, bringing as well S wave gives you another type of information. So this is a marine survey. We have a vessel. This is a vessel. Usually we have one vessel. And behind the vessel we have what we call a streamer. That's a streamer. Inside the streamer is filled with fluid, with oil probably. Each part here, the black strip, contains multiple hydrophones. Contains multiple, 12, 6, 24, depending on how you want the quality of your data. How you want to increase the signal to noise ratio. So that's how is it. Usually we have more than one hydrophone connected together, providing only one trace. They give you one trace. The group here also gives you another trace. This is how we do them. In this instant, if there is a ship, a vessel, towing behind a streamer and firing air gun, that's an air gun. Air gun is a type of source we use in marine that releases air, pressurized air suddenly. So that's how the energy travels. In this instance, it's hitting one of the layers and the energy reflects. These are what you see here. Here are the imaging point. I'm imaging this point in the subsurface. This is another point. So the number of points you image depends on the number of geophones you have. And the interval of these is your resolution. Interval between one point and another point is the resolution of your data. So what can I change in my acquisition to bring better resolution data? Distance of what? Between two groups of recorders. I can make this one smaller if let's speaking, let's say that the spacing between geophone group 1 and geophone group 2 is 20 meters. What is the spacing between reflection points? Huh? If the spacing between geophone group 1 and geophone group 2, the center of these geophones, hydrophones at least in this case, let's say it's 20 meters. What would be the spacing between reflection points? Huh? How much exactly? Half. 10, yes, that's 10. This is 10. So right now I'm only considering one type of acquisition where I have the vessel which is towing a line of streamer. The streamer contains hydrophones. That kind of acquisition, is it called 2D or 3D? It's 2D, yeah. You have the vessel towing behind the streamer. What I can make of change to make my data or the data require 3D? Huh? Add what? Another what? Streamer, another line. 1 line, 2 line, 3 line, 4 line. So that's how you conduct 3D data. The reflection right now we assume that for 2D the reflections are happening exactly from below the line. That's the line. This is the short point. The reflection, we assume they happen exactly from below, which is not usually true. So in reality, it's good to record 3D data. But why we don't record 3D data? What's the reason? What do you think? Expensive. Yeah, it's so expensive. The time constraint. Maybe you are not sure whether there is oil or not. You want to run very quick survey, reconnaissance survey to determine what is the general structure of the geology there in the subsurface. For those cases, it's good to acquire only 2D data. So this is the configuration. Behind there we have what we call a toy boy. That's a toy boy. Its main function is that to know, first of all, your navigation system. So So it sends information about where the line is, exactly, navigation. So you should know when you fire the shot, you should know at what XY location each hydrophone group was. It's very important. So this tool we have behind, it functions as two things. One of them, it lets the streamer to float at a specific depth below the sea surface. So it floats at specific depth.
But Doctor, is not affected by the wave? How the wave is moving?
Yeah, it affects. There is some effect, yes, and that we call feathering. How? Because if there is a wave coming, I expect my line to be straight, but there might be some feathering. I don't want to go to the depth, but that's a good thing. Yeah, waves, surface waves, sea waves, tides, they might affect the line position. Yep. It could be at depth, at an inclined line, but it's preferred to make it at one line for simplicity of processing the data later on. If you make it inclined line or having a dip, it's fine, but you need to know exactly what is the depth of each group, and it consumes some processing time then. You need to process them in different way. So that's the acquisition configuration. It's way cheaper acquire marine data than land data. Well, what's the reason? What do you think? The simple reason is basically, and the land data, we need a lot of labor work, a lot of people to move the cables, move the geophones. Whereas in marine, everything behind the vessel is doing everything, and we just start the acquisition. And usually when they acquire such data, we'll see some announcement. And in Oman, north of Oman, in Gulf of Oman, whenever they acquire seismic data, they told the fishermen around the area that, oh, you don't have access to this area for a couple of days or a couple of weeks, or whenever the vessel is closed. To some specific area, people will not have access. If I'm acquiring data, let's assume that this is the area I want to cover. The ship moves like that. It moves, this is the area I want to cover. So I need to go back. So what they do, the ship has a turning angle. It cannot exactly wait and turn back. So it has some turning angle like that. So it moves here and record again. So while it's moving back, to save time, it's best to record, and so on. So this is my area I'm covering. That's how it's done in marine data. In this specific case, I'm acquiring what kind of data? Is it 1D or 3D seismic? Sorry, 2D or 3D? It's 3D, I'm covering big area. Yeah, I'm covering a big area. I assume that this is the ship. It has behind, let's assume 4 cable lines. It has behind 4 cable lines. This is the marine acquisition. The land acquisition is more complicated. The type of sources we use in land, there could be either impulsive sources. By impulsive sources, I mean that the source signature you have is something like that. When you hammer the ground, the signature or the wave that you are sending to the earth, it has such signature. This is time domain. That's the amplitude. Amplitude is related to the energy you send. The harder you hit the ground, the more the amplitude is. Whereas for vapor-size, it's an impulsive. It's something like that. This is the zero, positive, negative. The energy sent by vapor-size, it's called an non-impulsive. This is impulsive source. They have some different characteristics. So we have non-impulsive, which is vapor-size. Vapor-size is vacuum. It has a plate the plate is attached to the ground, the vibrosize or vibrator lift its weight against the plate. So it's almost like raising your back tires. Raising your back tires and lifting all the truck on the plate. And start with simple frequency. Start with a frequency of, start shaking. So start with a wave of a signal, we call it sweep. And it's zero, at zero time, this is time is increasing, frequency is low. What kind of frequency is that? We call it sweep. So often we use not only one source at one vibrator in one point, we use multiple vibrators. Or even in the same point where we have the geophone, we combine multiple geophones together. And the objective is just simply to increase the signal to noise ratio. In the field I was with, doing my summer training or internship, they were acquiring data with 4 the vibrosizes in one point. So if I have, let's say, if I have 4 vibrosizes, they align in one line, that's 1, 2, 3, 4. Which one, where is the exact point where the source is? Huh? In the middle, exactly. That's where the middle point, that's the center of gravity of this configuration. ها؟ بيكون في الوسط. عند الثلاثة. That's easy. So usually they have with some specific distance 12.5 meters between one and another. And the driver does not do anything. He is only having the steering. He's only driving. That's the easiest job. They bring anyone, not necessarily a geologist or geophysicist. They train them for one day. Your job is only to drive. Only to drive. Because in front of their screen there is a big monitor, tells them where to move and tells them whether they are in the right position or not. Everything, how they shake, how they move, and how they connect together, they are controlled by some geophysicist back in office. They don't have gears, just 2 gears, forward and backward. Just forward or backward. And I drove one. It's nice to drive it because you just use the steering and see whether you are in correct position or not. Yes. And sometimes they repeat the measurements. They have to repeat it if there is some inconsistency. Yani they are firing together. They are so synchronized, even there should not be a simple difference, millimeter difference between those vibrosizes. It's almost like 5 or 4 people talking at the same time saying the same thing. Can we synchronize ourselves? It's hard. So they should get synchronized. Exactly. If there is some insynchronization, a variation, they have to repeat the measurement. So again, finally, because I'm doing land acquisition and a lot of labor work involved, and sometimes we need even legal people. In the crew I was in, there was a person, Iraqi person, who was so يعني شخصيته كانت قوية فخلوه هو الليجل بيرسون. ايش الليجل بيرسون؟ أن مثلا حابين يسووا acquisition في منطقة في بيوت أو مزرعة. There is a garden nearby. That guy who owns the garden, he says, no, you cannot access my garden. I cannot allow you to access my garden. So instead of paying these poor guys, let's give him one cup of tea and let him happy and then you can access his garden. In USA, in other countries, it's so difficult because they're, sorry about that. I should have switched my phone. Sorry about that, made it silent. So acquisition cost is almost 10 times as more expensive as marine acquisition, considering the same size. Considering a size of, like, let's say 10 kilometer by 10 kilometer in marine in comparison to one inland. The land acquisition is way, way more expensive. That's a vapor size. That's what you see is a vapor size. Where is the plate? Where do you see the plate? That's in the middle. It has a big plate. That's the tires. It has a control system, signal system, everything. Once it starts deploying, it raises the back tires. The back tires get lifted. All the weight is on this plate. So I was saying the signature sent by vapor size is non-impulsive. The reason being it's non-impulsive, it has a signal characteristic as shown here. That's what we call sweep. Sweep could be upsweep or downsweep. What you see here is a sweep that starts from low frequency, let's say 6 hertz, and start increasing up until 110 hertz. What kind of sweep is that? Is it upsweep or downsweep? That's an upsweep. You are starting from low frequency to high frequency. So this is a sweep. That's a sweep. What you see here is a sweep. So in case if I have, let's say, 2 layers, that's 2 layers, this is my vapor size. The vapor size sends this signal, or that signal, what you see, sweep. Sweep could be upsweep or downsweep. Which one is you think easier to deploy, upsweep or downsweep? Upsweep, yes, upsweep. You can start, once you start running, you can start running slowly, then you can increase. That's how even cars move. Cars start with slow speed, then they start getting faster and faster. The opposite is not possible. So the vapor size signal is the one you see there, the first signal. All of this signal, it goes as a train of waves into the ground. Once they hit this interface, what happens to them? They reflect back, am I right? And the angle of incidence is equal to the angle of reflection based on Snell's law and Fermat principle. So once it's reaching, going back, this geophone will record a train of signal. It gets received after some time, basically, not exactly that, let's say. It receives some signal like that. Why it's some similar to that instead of just a pulse? Because this is the signature of the energy you sent. أنا يوم أتكلم أقول يا فلان بتسمعني خليل جمعة محمود؟ لا تسمعني، أنت قلت لي يا فلان. أنا سمعتك قلت يا فلان، ما قلت خليل جمعة محمود. That's the same principle applies here. I sent a sweep. If I send a sweep, this goes, whole the sweep goes to the ground, returns back as a sweep. It changed its shape a little bit. That's what I said. It changed its shapes because Earth eats up. Earth will change the source signature. يعني لما أتكلم الشخص أنا يمكن قلت لك كلام وهو بيسمعني شيء ثاني، يقول لي يمكن قال لي كلام ثاني. That's the same applies because maybe there was an obstacle كان في ريح فما سمعني زين. The same applies there in the earth. The earth usually eats up high frequencies. The high frequencies, they cannot go very deep. Attenuates, earth attenuates high frequencies. So it reflects like that. This is what we call non-impulsive. This is impulsive. زين هذا أول يا رب. عندي بعد هنا جيفون ثاني. So here for the sweep This is first geophone, this is second geophone. It arrives after some time because it took longer time. That's the signature from the second reflector. This is from the second reflectors. So what you record finally is the sum of these two. Final يعني مثلا هذا خلينا في نفس الجوفون هذا مثلا كم استقبل؟ كم image استقبل؟ two different, one from each reflector. So let's say assume this one instead of this one, this geophone, this first geophone again, this geophone is recording both of this signal. This one and this one. 1 and 2. The final record it receives is something long like that. This is 1 and it continues with the second one. So you cannot recognize where is the second reflector. Can I? كأني أجمعهم مع بعض. هذا أجمع مع هذا. I'm summing them up. It's hard then to recognize where exactly the point of second reflector. From where, at what time reflection from second layer appeared or received. Again, the same example. This is what we call the sweep. It's starting from low frequency to high frequency. This is the reflection from the first layer. It's a layer. It's appearing here. I'm having a layer. The upper layer having a lower acoustic impedance, having a lower value of velocity times density. Acoustic impedance means velocity of the layer times the density of the layer. So it have a positive reflection coefficient. Here, one layer, another layer. One layer, another layer. Which layer you think has a higher acoustic impedance? This one or this one? Second, yes, because this is negative. The velocity times density product in the second layer is larger than the first layer. So here I get a reflection exactly starting from here, another one starting from here, another one starting from the third layer. Finally, I sum them together. 1, 1, 2, 3. That's the sum. If you see, this is what you receive, by the way. You don't receive these individual ones. What you receive? You receive this product. The trace is recording this energy. You are only seeing this. If I ask you, without having any knowledge about the number of layers, how many layers are there? Looking to this green trace. I can't tell. So someone says, why then we don't use a hammer or a dynamite? Yeah, if you use hammer and dynamite, it gives you something like that. So this is, that's 1, maybe 2, 3. That's if you use a hammer or a dynamite. Whereas the vapor size gives you this signal. But there is an interesting thing. There is a process in geophysics called correlation. There is a process in geophysics called what? Correlation. So in correlation, we cross-correlate these trays with the sweep to produce for me what? This signal. It's nice. You see, this is here. This is here. That's here. So my question, if there were 2 layers adjacent to each other, would I be able to descend them together differently? No.
I have questions when you have these sweeps and these signals. How can they know if they have refractions or reflections?
That's a good question. I can tell that from gathers, shot gathers. You cannot tell anything what type of image is that based only on one trace. So you need a lot of traces together. So you can tell whether there is a reflection or not, or if the energy is reflected energy or refracted energy, or is it a Rayleigh wave, is it like an air wave, what exactly is that? We need to have a lot of traces together, like what you did in the lab, last lab. I'm not sure whether you completed the lab or not. That's what we were doing in the last lab. So in the last lab, if you see, there are a lot of traces, if you see that there is a hyperbolic feature, that could be a candidate for reflection. If you see a linear feature in the upper, that's either direct or refraction.
But Victor, about these signals can be by the amplitude, the high amplitude and low, determine the velocity and density.
Yes.
Because if you know the velocity and density, you can be determine the model or the layers what you are typing.
True. That's true. Yeah, sometimes you can guess what is the type of rock you have based on their amplitude. Provided, I don't want to go to the details, provided once during the processing, once you were analyzing the data, you haven't destroyed amplitude information. يعني هم يعالجوا البيانات ما يهتموا بالامبليتيود كثر ما يهتموا بالشكل. فيمكن يسوي فلترنج يقتل الامبليتيود. إذا قتلت الامبليتيود عبارة ما عرفت ايش الجيولوجيك روك. ما ترجع للروك بارت للفيلوسيتي ولا الدنسيتي. I have a question for you. What's your name again? Nasser. Why this is up whereas this is inverted version of this one? It's pointing to the down, this is pointing up.
Depends on the velocity of the
Yeah, somehow, but to make it more clear, better answer. These two are pointing up, whereas this is pointing down.
change in the layer will be the one, and also the incidence of the engine.
It's not the incident. It's because of the acoustic impedance. Yeah, that's how is it, because here I'm moving from softer layer to higher layer. Rock and density, the product of density times velocity is lower here than here. It's like what you see there, the density and velocity product in this layer is lower than the lower layer. That's what we call reflectivity series. We'll talk about again some coming slides what's reflectivity series. So here it's positive, it's negative, it's positive again. Huh? Somewhere there? Yeah, if we have, for example, let's say another layer, another interface. But definitely you cannot go very, very deep. There is some limit. We can image up until, for example, let's say 5 kilometer, 6 kilometer using vapor-sizes. Whereas if you use the earthquake data, you can even image the whole earth. Because earthquake, they send large energy data. Whereas vapor-size and hammer, it can only go up until 20 meters if I hit with a hammer. So I cannot go like say, oh, does it change? What is the next thing? For indefinitely. It's not like that. So here is, this is the real data. What you saw before were just simple data. These are real. It's a vapor size with a lot of traces. A vapor size with a lot of traces. So this is the sweep. You see the sweep? It's starting from low frequency, increasing the frequency. It's running for how long? How many seconds? 10 seconds. Going from here, continuing from here. The frequency is increasing. The frequency is from what to what? 6 to 60 hertz. Here it's low frequency at early times. At later times, it's at 10 seconds, the frequency R maximum, 60. That's what I send to the ground, and the ground record whole of this section. 1, 2, 3. My recording time is 15 seconds. My recording time is 15 seconds, listening time. I let the geophones record for how long? 15 seconds. So it's starting from 1 second, 2, 3, 4, and so on, up until 15 seconds. So this is long section, long weather, but my question, can you discern anything? No. It's similar to this. Here I had only one, whereas here I have how many? Many of them, side to side. Because each one represents a group of receivers, a lot of geophones, or maybe one geophone. Depends on your acquisition parameters. What I do, what is the process we said? Correlation. I cross-correlate this recorded data with the sweep. That's the final section I receive. This is the final section I receive. So back to the question you said, how I can discern whether this energy is reflection, refraction. You see these hyperbolas? What are they? Reflections. What is this energy here? Refracted energy. What is this energy down inside? That's ground rule, that's surface wave, in noise. Still, this is not a seismic section. That's still not a seismic section, keep in mind. We do still a lot of analysis. We do velocity analysis, stacking, and so on. So many things to convert our shot gathers to seismic sections. Same back to the questions. In a gather, that's where, if I ask question, where the source has been in this data, where the source location is at 0. The direct, because the direct is the energy that travels straight from source to receiver. That's the direct, the yellow lines. I have geophones in both sides. I have geophones in both sides. What is the green? Refracted. So refracted is that. The critical angle is somewhere here. What is that angle here? Or what that distance is? Crossover, yes. Crossover, refracted, comes before the direct. What are these? The red one? Primary, reflections. What is the blue one? Multiple. This is a multiple. You see, the steeper this curvature of the hyperbola, those are hyperbolas. They are following equation of hyperbola. They are reflected energies. One of them, probably this one or this one, is double of the time. From here to here is double of this time. Because it's what? A multiple. 1, 2. 1, 2. That's a noise. A multiple is a noise. What is this? We know so far that the gentler the slope, the higher the velocity. The steeper the lines, the low velocity. So you see this line, if you take 2 points, calculate the distance, divide it by the time, how much you think you will get? What velocity you think you get? Huh? What is the velocity of sound? Huh? 3,000? Not 3,000. Remove 1 0. 300, yes. That's about the velocity of sound. يعني لما ايش الاريا that's the airwave. أنا يوم أسوي انفجار أو الفايبريتر يضرب الموجات تمشي كل اتجاه، حتى في الهواء تمشي. Could you tell me one way of in the acquisition stage to minimize this noise, air wave? Perfect, yes, that's how is it. You bore your geophones. You can what do? You bore your geophones to remove the air wave. At least, not, you cannot remove ground rules. The ground rules, they move even in the rock. So this is ground rule. That's a ground rule. It looks like to me ground rule having a higher or lower velocity than air wave. Lower, yes, they are steeper. What is ground rule, by the way? Rayleigh waves. Yes, that's true. Surface Rayleigh waves are ground rules. That's what you see. It's easy to calculate velocities of linear features. This is a linear feature, that's a linear feature. You just take the reciprocal of slope. Reciprocal of slope gives you the velocity. It's hard to get the velocity of reflections. It's not as easy to get a reflection energy. So there is a video, I recommend that you watch the link in YouTube. It's a bit long video about how seismic acquisition is conducted. Here we see two vapor sizes working simultaneously or concurrently together. Here we have plenty of them. They are actually having one point. They are working simultaneously. They have one center point. How many are there? 2, 3, 4, 5. So you were asking where is the center of gravity or central point? Maybe at the location of vapor size 3. You see this pile of cables. What are they? What do you think are they? Geophones. In our setup we have 24. Whereas here, big piles. Behind you see red cables. What are those red cables? They are connectors. They connect the cables together, geophones together, to those connectors. They are preparing themselves, preparing the setup, the equipment to move to the acquisition stage. It's tedious work. I pity the workers there, the laborers. In UAE, at least they employ Filipinos, Bengalis in Oman. Who you think work on this work? Huh? Omanis. Yes. They are Omanis. They don't know anything about geophysics or geology. They want to drop it quickly, tack, with their foot. As like they want to finish the job. But there is one observer. Observer himself is not, he's looking anything going bad. And the job is tedious. It's really tedious. You see here there are some workers preparing themselves to carry these geophones. They are here doing testing. Before they go to the field, they need to test the geophones. Are they fine? Is there any electric failure with these geophones? And finally, once we acquire the data, we do all the processing. We do stacking, first velocity analysis, then stacking the data. Each CMP gather will produce how many traces? One trace. Each CMP gather, what I mean by CMP gather, this is a source, receiver. 1, 2, another one. Let's say there is also one here. I'm imaging which point, the same point in the subsurface. The only difference is the offsets. The offset is different between these pairs. What's the number of fold in this case? 3. The number of fold is 3. That's a repetition of what I have talked last time. Please watch the videos at least. So the fold is 3 because I have 3 repetition of measurement. I'm measuring the same. I sum them together. Each one, this one, if I plot them time versus offset is this spacing. This have the lowest offset, so I get a reflection like that. Then another reflection. This is from the second one. 2. This is from the third one. That's what you get. What is this line? What we call this line? Hyperbola. That's a reflection. We do enamel correction. Enamel correction is bring this one flat. Then we do what finally? Stack them. All of this we're going to be 1. So,
So what is about the difference between refracted in this wave and reflection? How to determine the refracted and reflected?
yeah, I'm here just drawing a reflection, but if there is a refraction, it will show up like that. A straight line. I'm ignoring the reflect. I'm not showing the refracted energy. If there is a direct, it might show like that. Then it will be overcome by, here is the critical distance. Here is maybe, sorry, crossover is, here is the critical distance. So each these trace, what you see here is not from one pair of source and receivers. It could be from many pair of source and receivers. يعني هذا بوينت واحد، كانوا 3 جمعتهم مع بعض أعطوني هذا التريس. هنا كان في نفس الشيء 4 و5 مع بعض جمعتهم، يعني كده أكثر من واحد. You put them side to side. That's stacking. That's the final section. You get some display like that, like what you see here or here. This kind of display, they are the same data. I'm changing only the display. If you go search in Google, seismic data, seismic sections, you could either see such displays or such displays. This is wiggle trace. That's what we call a wiggle. That's variable area. They are the same. What is the difference between these two? What's the main difference? Could you point the main difference? Huh? I shade one side. I shade above probably 0. And if I draw a line where 0 amplitude is, above 0 I make a shading. Color it black. That's how is it. This is a different. Which one? Some people they like this display. Some other people still like such display. For my case, I don't like both of them. I like what I call variable density. This is a variable density. It's a big section. That's a big section. That's variable density. Variable density can have different colors. It's, for example, here I'm using grayscale color. The color either black or white. Black or white. So black is very big positive, white is big negative. The trace going positive or trace going negative, like what you see here. It's going positive or going negative. Something like that. So this is positive, this is negative. This is similar actually to what you saw here. But I do one more step. I shade between them. I shade between these traces. I make it like an image. This is what we call variable, and this is the most common one. The only difference is the type of color used. Sometimes they use grayscale, white to black. Sometimes they use different colors. This is a different color, green, red, and black. So the 0 amplitude probably is green. The maximum positive is red. The maximum negative is black. The maximum positive is green, red probably, the zero is red as a green, and so on. And they change, they becomes more strong, less strong. This is very strong, here I'm seeing very strong reflection, again here I'm seeing very strong reflection. What that indicate? Huh? This is the sea level. This sea level, huh? No. What that indicate? What could you think? Could you remind me of your name? Huh? Shakar, what do you think? Geologist? Petroleum engineer? What do you think? Why there is a variation? Here I'm not seeing strong reflections, whereas here I'm seeing strong reflection. These are reflection data, not refraction. Huh? Huh? No, no. Yes? What? Not geologic feature. Not geology, another thing. Huh? Density. Yes, that's يعني الفرق في الاكوستيك امبيدنس بين هذا الصخر واللي تحت عالي جدا. The difference in acoustic impedance is basically the product of density times velocity. So reflectivity series is large. What is reflectivity series? If I go back, is it far away or, yeah, this is reflectivity series. What happens if this change in acoustic impedance is very large? What happens? You will get a large one. So if this is large, this becomes very large. يعني بعدين خلينا نحط أكثر من واحد جنب بعض فبيطلع لي لون غامق. لأن الرفلكتر is strong reflector. The acoustic impedance between these two layers is big. What if there is no acoustic impedance? What if there is no physical difference between, huh? No reflection. خط مستقيم. It's very simple. Yeah, it's very simple. If ما في اختلاف في الصخر الاكوستيك امبيدنس physical property الخط بيكون كده مستقيم. ليش اللي ما في هزات؟ لأنه ما في تغير. نفس الصخر. إذا الاختلاف بسيط ايش بيطلع لي؟ شيء بسيط. هزة صغيرة. إذا الاختلاف ضخم طيب في يمكن هناك في لاير مختلف ومع ذلك الاختلاف كبير مع ذلك الهزة صغيرة. ليش؟ هي آخر شيء في التايم. ليش؟ ها؟ energy loss. That's the energy loss. Yeah, you see geophysics is really, wow. Blow my mind. Yeah, we tackle all these informations in other courses, in like data processing in applied geophysics 1.
Sometimes when you make it analyzable models about these secrets and red graph, maybe you have something bold options.
Yeah, where there is, if I go back,
So when the channels will be have.
yes, they could be channel because channel having a different rock property. The basic principle is there is a strong change in rock property, physical properties, which is density times velocity. We already said reflection is responsive to these two changes, density and velocity, whereas refraction is only responding to change in velocity. Yeah, that's true. There is a fault. That's the same layer, faulted, this descended down. There are many other features, geologic features. There could be a fault. There are many other things. I'm not a geologist, so I believe geologists, they can do better interpretation than mine. But however, I can highlight geophysical features if there is something wrong in my data or wrong or not. So I see something called DHI. DHI refers to what? DHI, direct hydrocarbon indicators. usually even from your image you can tell whether there is hydrocarbon or not. But we'll keep it to some later time. So back to the acoustic impedance, to the topic of acoustic impedance. What exactly is acoustic impedance and how we can define reflectivity series? How much energy going to be reflected? What is the amplitude of reflections? And how much of the energy going to be transmitted to deeper layers? So it's all based on the what we call acoustic impedance. We need to have change in both density and velocity. If there are two different rocks, you have two different rocks, yet their acoustic impedance is the same, do I get reflection or not? I repeat myself. So the question is, if I have two different rocks, still their acoustic impedance is the same, would I get reflection or not? No, I don't get reflection. I don't get reflectivity. There is zero reflectivity. Reflectivity is basically how much energy. That line you saw before, that's called the reflectivity series. How much reflection you get. It's based on this simple equation. Acoustic impedance of deeper layer, if I have two layers, deeper layer minus acoustic impedance of the upper layer divided by their sum of the acoustic impedance of these two layers. This gives you a value. That value represents how much energy will reflect. But keep one thing in mind whenever we talk, or shall I say it, this is only valuable for normal incident. عارفين normal incident؟ يعني الانرجي يروح ويرجع. إذا جاي على انجل هذا ما يصير. فيها قوانين شوية معقدة أكثر. This is possible only for normal incident. This is possible only. This is how much energy going to be reflected. So how much is transmitted? If I have the total energy, let's represent it as 1. رقم 100 ولا 1. إذا هذا كمية percentage of energy, not رقم كبير يعني percentage. This is value. The maximum is how much you think? Based on this formula, what's the maximum value? Yeah, don't be shy. It's 1. It's either 1 or minus 1. It's either 1 or minus 1. Based on the equation you see, because the sum, the division, the subtraction divided by the sum, that is always 1 or minus 1. If it's 1, it means what? What happened to the energy? Huh? If it's 1, it means what? All the energy reflected. ما بقى شيء يروح للديبر. Is it even minus 1? كله رجع بعد، لكن ضرب باسم خليل ورجع باسم سعيد يمكن. ليش؟ لأن صار العكس، هذا جاهني وهذا جاهني. فهمت؟ الرفلكتيفيتي سيريز الفاليو من -1 إلى 1. إذا كان 0 الرفلكتيف، إذا كان 0 عبارة ايش؟ ها؟ ايش؟ كله راح. كل يجي transmitted no reflection. ما في layer. متى بيصير هذا؟ هذا يصير يوم ان هذا الفالي هذا above is 0. متى يصير 0؟ هذا الاثنين متشابهين. نفس اللاير يعني ما في ريفليكشن اب. كمان you should have some common sense then. وش يحصل يوم ماينس؟ يوم 1 عباره عن كله رجع، لكن هو الانرجي شكله كده جاي، هذا الانرجي رايح ضرب هنا ورجع، في عندي جيوفون قرا الانرجي كده. خلينا let's assume that this is 1. What about minus? That's the same. All the energy is reflected, but this geophone here وش الفرق بينهم؟ العكس. 180 phase shift. That's what we call 180 درجة تغير. So this is what R. متى يحصل؟ أكون لازم هي تصور لي معه. So that's what does mean minus 1. That's what it's the opposite of this. It means that يعني إن هذا مثلا كان V1 density 1 V2 density 2 هذا كذا بيعطيني هذا. إذا عكستم هذا راح هني الصخر هذا طلع هني وهذا نزل تحت بيعطيني minus 1. That's the reflectivity series. There is also how much energy transmits. How much gonna be transmits? There is some transmission. So transmitted energy is as such. 2 of acoustic 2 times the product of density times velocity of the upper layer divided by the sum of acoustic impedance of the layers along the interface, any interface. That's how much energy gets reflected. Transmitted. How much energy gets transmitted to deeper layers. نعم.
About the second, the negative.
Uh-huh.
Can be happening in the hammer, the same when you have negative?
Hammerhead?
Yes.
Yes, any type of source. It's not dependent on the type of source, it's dependent on the geology. But keep that in mind. يعني الامريكان شوف التعقيد يعني الامريكي يوم الصخر اذا الصخر يزيد في الصلابه هذا كذا يسموه بوزيتيف يعطوا هذا الشكل. الاوروبيين الواحد يعطوا هذا الشكل. ها ما فاهمين مع بعض. ايوه بيدو اي شركه اي كونفنشن يتبعوا. ها الامريكي ولا الاوروبي؟ What do you think الامريكي لا يتبعوا الاوروبي. السبب انه هم جزء من شركه شل شركه اوروبيه joint venture between UK and Holland. So they follow the European standard. يعني هذا الصخر هنا الصخر الصلابة تزيد عبارة عن acoustic impedance upper layer is lower than the deeper layer. The European will plot it like that. So American will plot it like that. فنشوف مثلا في النظام ماشي على النظام الاوروبي شفت الهزه كده جايه عباره انها هذا في صخر اعلى منه وصخر تحت. الصخر اللي اعلى في اليوروبيان ستاندرد الاكوستيك امبيدنس اقل عن اللي تحت. الفيلوسيتي تايمز density of the upper is lower than in the European standard. So people ask what standard you were following. انه سهل ممكن تغيره ببساطه اذا عندك الداتا. تغير الفيس -1 تضرب الفيس الانجلز -1 تغير عندك الفيس. شيء يعني ما ياخذ حتى بالكمبيوتر. this is the conventional model. What you see here, that's how the geology works. So this is the geologic section. That's a geologic section. What I have, different rock layers, shale, sand, shale, the sequence of shale and sand. So you have what I call velocity, a velocity log, and also I have a density log. In geophysical log measurements, that's a velocity log and a density log. What happens if, what product I get if I multiply these two logs? Acoustic impedance. I get the impedance or acoustic impedance. So this is the acoustic impedance. I'm moving from high acoustic impedance to low acoustic impedance. Shale has a lower, it's a softer rock than sand. So I get, let's do the calculation. What this value is basically what you read here. That's exactly that value. So that's what you send to the ground. This is what we were sending, the wavelet. That's the wavelet. It goes, reflect back. So it's a convolutional. It's not multiplication. It's more than multiplication. It's more complex thing than multiplication. So it got convolved with these traces, with this reflectivity series. فهذا هي، هل بيكون شكله كده ولا العكس؟ العكس، يجي كده. This wavelet. This is the source. Vapor source شكله كده. Vapor source. Hammer source, dynamite source شكله كده. هذا الشكل. Vapor source شكله كده. السنتر هذا الزيرو، الماكسيمم امبليتيود as the zero. Whereas dynamite and other sources, hammer source, they have impulsive source. So it convolved with this reflectivity series. تشوف الأحمر أول أحمر من هنا. It's scaled version of this wavelet with this reflectivity series. I'm going from low acoustic impedance to high acoustic impedance. Then the opposite, from low to high, and so on. That's how is it, and that's the final trace I get. That's the final trace I get. So this is how it works. You have a reflective. This is your source signature. That's the image you are sending. It's getting convolved with the reflectivities, and you are producing a seismic trace. A layer, another layer, another layer. You are producing different layers, 1, 2, 3 layers. You're convolving your reflectivity series with what we call source wavelet or source signature. And in geophysics, there is a process called deconvolution. We try to get, even not knowing the source signature, we can extract it. We can try to find what kind of source they send to the ground. However, where do you think this could be used a lot? This type of info, where I can use them? Well logging, yes. In well logging, this is one of the main processes they do. They try to tie between seismic and wells. السايزميك ايش اللي ريزوليوشن على الويل ولا السايزميك؟ طبعا الويل. Which one covers with much bigger area? Seismic. Which have higher uncertainty, wind or the seismic? Seismic has a higher uncertainty. So we do this tying. لما أنا عندي الجيولوجي وهذا التريس اللي أجيبه بالنهاية هذا من الجيولوجي ما له علاقة بالسايزميك أبدا. من اللي عندي ويل سويت طلعت تريس، سويت كني تريس. عشان كده يسموه synthetic. يسموه ايش؟ synthetic. What's the meaning of synthetic? ما أصلي. Not real one. Synthetic. You say, oh, this cloth is synthetic. ما بشتري، أنا أشتري بيور 100% cotton. So that's your trace. That's the trace you get. You do what? At the same location in the seismic, you compare this trace with your seismic trace. How much they match? Definitely this is correct. عبارة إذا في خطأ هناك يعني الشخص اللي سوى بروسيسنج ما شال النويز. فعندك مثلا مالتيبلز ظاهرين ما شال المالتيبل صح. This is correct. This is from real data. ما شال بعض النويز ما شالهم. يمكن عندك ريفلكتر عندك كده امبلي ريفلكتر في السايزميك داتا not available here. Not available in the synthetic data. It means that you haven't done your processing properly. And that's a tool companies like PDU quality control their results. And CGG شركة ثانية contract هي تسوي تاخذ مبالغ من الملايين تشتغل حالهم على طول. هم يسووا processing كل شيء. منها يعطوا data size reflection data جاهزة. البي عندها geologist geophysicist who do interpretation, and the first thing they do at will tie check whether there is good thing or not, whether the data you got are they resembling the geology or not, at least in some few points where I have real data. And that's one of the reasons I don't go apply to 3D seismic from the beginning, because very expensive. I don't know whether there is oil or not. Let's do 2D seismic initially. Get an idea about the geology, about the rock types of rock, structure of the rocks, then move forward, make 3D. There is huge difference in terms of cost. Let's talk about resolution. What is resolution? How we can define resolution? How I can tell whether there are two different layers or I say I cannot resolve. هذا source signature. This is the source signature. You think usually how big is the source signature? What is the source signature size? How big is it? You think probably. I recently made this. What is that? برج what? برج الصحوة. Am I right? ودوار صحوة. That wavelet is as big as that. So it's not as, it's something, let's make it much better. This is a better representation. فإذا عندي two layers قريبات من بعض. I have two layers very close to each other. فايش يحصل؟ هذا اللايرز قريبات من بعض. هذا السورس هنا وهذا الجيوفونز. الانرجي بيمشي ويرجع وهنا الانرجي يروح ويرجع. I have two reflections. Each one is resembling the size of this wavelet. The size of this wavelet. If this is my trace, هذا من أول layer وهذا من ثاني layer. أنا اللي بالنهاية أحصله السم. فممكن سبب من الأسباب I cannot resolve. I see only one layer. Or sometimes I don't see any layer. They interfere constructively. أجمعهم مع بعض. هني كان positive, هني كان negative. There is a layer, I don't see it. So that's really possible. So here in this case, what you see, two energy reflected. That's the separation. One layer, another layer, and in the first case, the velocity is increasing. The acoustic impedance is increasing with depth. So this is from, let's say this is from, this is after reflection, after they reflected back. هذا أول layer، هذا ثاني layer. That's the source signature. Source hit this, the reflected, this reflected back. This, it hit this reflection, went back. And there is time difference. طبعا time difference لأن هذا بيرجع قبل وهذا بيرجع بعدين. لكن في مسافة، في time difference between them. I get the sum. What is the sum? That's the sum. I still can resolve. I can see two different things. If I bring them together, these reflectors, what I finally see, that's final product. This is first, second reflection, two reflections close to each other. Their sum is big. I get one big. So I cannot resolve it. Here, this layer, the middle layer has a lower acoustic impedance. The acoustic impedance of velocity 1 and velocity 2 is higher than the middle one. فايش بيصير هذاك يعكس، ينعكس الموجة جاية كذا بوزيتيف ترجع بتكون عكس. فعندي هذا that's one, where is it? That's one. You see it became the other direction. It start moving here. ليش راح العكس؟ لأن عندي acoustic impedance larger here. Sorry, lower than here. يعني this here is lower. Middle one is lower than upper one. The middle one has a lower acoustic impedance. Reflectivity series, one of them here is negative reflectivity series. So if I show it here, let's say these are the two layers. Fortunately, do anybody have tissues? One or two tissues? Unfortunately, I lost my rubber. Or there is one. That's fine. So for the second case, here that's the acoustic impedance. I'm moving from large rock to lower rock. What I get, reflective series, is it positive or negative? Negative. Reflectivity series is negative. Here reflectivity series is again positive. That was my signal. That was is supposed to retain like its original shape, but it retains like that. Here it's from low to large, it's positive, so it retains like that. Yani. You got it? It hits this layer and start moving up. So these are the two. This is from one layer and another layer. One is that. You see that one? That's the same, and without change. This is from, looks like this is from deeper. That's from upper one. Upper one is this dashed one. And we sum them together. What happens? At some places they interfere destructively. The final output you get is something like that. The final output, here I'm making them closer to each other, finally you get only one, this one. So if you get this one, you think that there is one layer. In here, you are still removing or decreasing the amplitude because they are almost opposite to each other. Reflection from upper and reflection from lower. They are opposite of each other. They get combined. So you get a lower amplitude, something like that. You think that there is, probably this is noise, there is no real reflection. So what is the condition that, first of all, what I can do to get higher resolution data? What could be done from my side? What could I change here? We'll finish soon before moving to, What? Wavelength? Perfect. We'll have wavelength of what? Of the source. You need to have to change the wavelength of the source. So this was my source. Why not sending a better source? Why not sending some source like, which one is better, this one or this one? A or B? B. ليش؟ لأن هذا عندي لو لاير كذا، ال A بيطلع لي كذا ها، وهذا كذا. في هني مع بعضهم، لكن إذا عندي الشكل كذا واضح عندي كم؟ 2 layers. ليش ما أرسل مثل هذه؟ ليش ما أرسل مثل هذه؟ ليش المعقدين احنا؟ نعم. نعم. Which one, by the way, which one has a higher frequency, this one or this one? Second one, yes. Second one has higher frequencies. So what is the best source? The best source in geophysics is a spike. شكله كده بس خط. Huh?
So why we use the first one?
Yeah, why then? That's my question. That's, you are smart. You are referring back the question to me. E. Yeah, somehow we go deeper. Yes, you will go deeper. If you send this one, it will decay quickly. It goes only 20 meters, 30 meters. As I said, ETH acts like attenuator. It finds high frequency, it eats up. Nothing left. So how I can go deeper? هذا نفس الشيء لل 5G. ليش ال 5G ما يدخل داخل البيوت؟ It has high frequencies. Signals of 5G are high frequency. You can get good signal outside, but you don't get good signal inside rooms, inside homes, because the frequency is high. And that's the reason some people are aware of 5G, because they think that they will contaminate or do something bad to their body. High frequencies, yes. We are going with higher frequencies. And until we go maybe gamma and beta frequencies, that can kill us. Yeah, that's the same principle. Even I say this one, which is not possible. يعني ما في جهاز ممكن يرسل لي بس مثل سيجنال مثل هذا. إذا ضربت بقوة ضربة قوية، إيش اللي بيتغير؟ هذا الأمبليتيود بيتغير بس. هذا بيتغير لكن ما ممكن أجيب سيجنال مثل سبايك في الجيوفيزيكس، أو ما في mechanical thing that can send you spike to the ground. إذا ترسل مثل هذا الجيوفيزيكس the best thing. It gives you detailed centimeter, millimeter resolution of the earth. There is no better than geophysics. عشان كده الالكترومagnetic الجي بي ار جراوند بنتريتنج رادارز يعطيك ريزوليوشن هاي لكن بس مترين 3 متر. عشان كده الجي بي ار طريقه ثانيه في الجيوفيزيكس يستخدم عشان يحدد اذا في بايب لاينز، اذا في ليك في البايبس، يعطيك صوره واضحه. نرسل موجات جيجا هرتز، جيجا هرتز نوت هرتز، موجات جيجا هرتز، بس تروح مترين 3 متر وخلاص. And that's the reason earthquake data, even the earthquake happens in Japan, I can record it here because it's traveling in frequencies lower than 1. Lower than 0.001. For these frequencies, very low frequencies, you need an equipment which is very expensive. And in geophysics and seismic data, we need a lot, thousands of geophones. So shall we go buy all these very expensive geophones? Earthquake seismology يعني في عمان عندنا 20 فقط محطة. 20 ولا 17 عادي، عندي 20 محطة ما عليه، كل محطة سويت ب 100,000، اشتريت الجهاز 100,000، ما مشكلة 20 هم. لكن في الايرثكويك سايزمولوجي استخدم جوفونات عادية. الجوفونات هذه اللي ما تقرأ كل الموجات، ما تقرأ كل الفريكونسيز. يعني الموضوع معقد. So it's not an easy topic. However, the overall takeaway from this slide is the final, what is the minimum separation? I said I can increase the resolution if I decrease the amplitude. Decrease the wavelength, increase the frequency, make better frequency source. There is a compromise. Shall I get high resolution shallow or get deeper data but not very, very high resolution? There is a compromise. How much deep you want to get your image of the subsurface? So the minimum separation depends on what? On your wavelength in the source signature. It's quarter, ربع of your wavelength. يعني إذا عندي خلينا نقول 100 متر، الويف السورس 100 متر، كم المينيمم سيبريشن المفروض بين اللايرز؟ ها؟ 20? That's true. Quarter of wavelength. Quarter of a wavelength. إذا عندي 10 2.5. زين إذا عندي لاير مسافة بينهم 2 متر. What is the minimum wavelength I should use? ها؟ تضرب في 4. ها؟ أقل شيء هذا. يعني ممكن يكون أقل لكن ما يكون أعلى. إذا أعلى you might miss, you cannot record it. The question again, maybe you lost it. Let's assume that the minimum separation between two layers is 2 meters. What's supposed to be the minimum wavelength? Huh? Or the maximum wavelength in this case? Maximum wavelength. The opposite way. Huh? 8. Can it be 9? Can it be 7? Yes. So that's the maximum wavelength. Based on this, that's the maximum. You to resolve 2 meters. Quarter of a wavelength. So 5 minutes are remaining. I want to ask you whether you have a question to what we covered. We're supposed to have a lab. That's totally fine. It's more important to cover the lecture parts. Especially I'm supposed to give you the exam during non-lecture time. Shall I give it to you? You do it yourself? Huh? Next week we'll move to gravity. And if we move to gravity, I better give you a lab on gravity because I think the lab you did on velocity analysis, this is sufficient. Yeah. Yes?
The lab on velocity, the X is supposed to be the same for all layers, right?
Yes. You can choose the same X as long as the X, the hyperbola is cutting that X. يعني ما عندي مساحة هذه يجيني استغرب هذا ايش مسوي؟ حروس؟ So إذا أنت اخترت X هني مثلا هذا ريفلكشن خلاص ما واصل غلط. لازم الإكس يقطعهم كلهم، أو تختار هني إكس، هني إكس مختلف وهني إكس مختلف.
Also, when they are big, they're getting the velocity lower.
Maybe there is something wrong. Someone told me something, but I really got busy.
So everyone is the same.
Okay, so let me check it myself. Let's see how many slides left, because we need to finish this part. Yeah, not much. That's good sign. There is only few slides and they are belonging to the same topic. So let me review it.